Okay, think about this for a second. What if I told you that everything around us, everything that feels so solid, is actually 99.999% empty space?
It sounds completely counterintuitive, doesn't it?
It really does. And that realization that almost all the mass is packed into this tiny, tiny core came from one groundbreaking experiment. Welcome to the deep dive.
Today we're looking at Ernest Rutherford's gold foil experiment. It really did flip our whole understanding of matter on its head.
Right, so before Rutherford rocked the boat, what did scientists actually think atoms looked like inside? There was a dominant model, wasn't there?
There was, yeah. It was called the plum pudding model,
Oh,
proposed
yeah.
by J.J. Thomson around 1904.
Plum pudding, okay.
Yeah, picture like a blueberry muffin. The idea was the atom was this sort of sphere of spread out, uniform positive charge, that's muffin, and tiny negative electrons were just embedded in it like the blueberries.
So the positive stuff in the mass were just sort of diffuse, spread all over.
Exactly. That was the key assumption. And our mission today, really, is to unpack how a relatively simple experiment completely demolished that idea
Yeah.
and showed us what atoms really look like.
It's amazing how science progresses. Before we get to Rutherford, we should probably mention the really old ideas, like the ancient Greeks, Democritus.
Sure, atomos, the idea of something uncuttable. That was purely philosophical, though. No experiments.
Right, just a concept. It wasn't until John Dalton, maybe early 1800s, that we got the first scientific atomic theory based on actual observations, like how elements combine in fixed ratios.
That was a huge step, moving from philosophy to quantitative science. And then came Thomson's plum pudding model, which
Yeah.
was, the accepted picture of the atom's internal structure.
And crucially, what did that model predict would happen in an experiment like Rutherford's?
Well, if that positive charge and mass were really spread out and diffuse, like a jelly or a cloud,
Okay.
then if you shot something heavy and positive, like an alpha particle, which is basically a helium nucleus, quite hefty at this atom, it should just punch right through. Maybe get nudged slightly off course, but nothing dramatic. Thomson himself used an analogy like a cannonball going through the side of a wooden house. It might slow down a bit, but it goes through.
Okay, so that sets the stage. Then in 1909, Rutherford, along with Hans Geiger and Ernest Marsden, they set up their experiment. Tell us about the setup.
It was quite clever, actually. They took a radioactive source that emitted these alpha particles.
The cannonballs.
Right, the positive projectiles. And they aimed them at this incredibly thin sheet of gold foil. I mean, really thin, just a few thousand atoms thick.
Wow, that's thin.
And around the foil, they placed a screen coated with zinc sulfide, which flashes, it scintillates whenever an alpha particle hits it. So they could see exactly where the particles went after hitting the foil.
So based on the plum pudding model, they expected to see pretty much all the flashes concentrated directly behind the foil, right?
Exactly. Maybe a tiny bit of scattering, very small angles, but basically straight through.
But that's not what happened, is it?
Not even close. I mean, most of the alpha particles did go straight through, which was
Mhm.
important. It showed atoms were mostly empty. But this was the stunner.
Yeah.
A small number, maybe 1 in 8,000 or so, were deflected at really large angles. And some, incredibly, bounced almost straight back towards the source.
Straight back.
Straight back. It completely contradicted the plum pudding idea.
Rutherford's reaction to this is quite famous, isn't it?
It is. He said, it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you.
That perfectly captures the shock, the paradigm shift. You just don't expect tissue paper to deflect a cannonball.
Absolutely. So these results, they forced Rutherford to rethink everything. He realized the only way particles could be deflected so violently or bounce back was if they hit something incredibly small, dense, and positively charged within the atom.
So not a diffuse cloud of positive charge at all.
No. He concluded the atom must be mostly empty space. That's why most particles went through.
Yeah.
But at the very center, there had to be this tiny nucleus containing almost all the mass and all the positive charge.
The nucleus.
Right.
That was the birth of the nuclear model of the atom.
That's it. It completely overturned the plum pudding model. And this discovery wasn't just, an academic correction. It laid the foundation for Niels Bohr's model, just a few years later, for quantum mechanics, nuclear physics.
And even things like nuclear energy and medical treatments we rely on today.
Precisely. It all stems back to understanding that atomic structure, which Rutherford revealed.
It's still kind of mind-bending to think about it, that the solidity we feel is an illusion created by tiny nuclei and electron clouds in mostly empty space. 99.999% empty.
It truly is.
So this deep dive really highlights the power of experimental science, doesn't it? One carefully designed experiment, observing something unexpected, can literally change our entire view of reality.
It's a perfect example. It shows how science advances observation, surprise, rethinking. So maybe a final thought for everyone listening. The next time you pick something up, or just look around,
Yeah.
remember that what you're seeing and feeling is overwhelmingly empty space, defined by these tiny, incredibly dense nuclei discovered because a few alpha particles bounced off some gold foil back in 1909.
Yeah.
How does knowing that really change how you see the world?